Hello and good day to you. Come, pull up a chair as we venture into exploring the fascinating subject of cosine similarity in embeddings, inspired by the insightful research paper titled, "Is Cosine Similarity of Embeddings Really About Similarity?" by Harald Steck, Chaitanya Ekanadham, and Nathan Kallus from Netflix Incorporated and Cornell University. Now, cosine similarity has long been a staple in the toolkit for measuring semantic similarity between high-dimensional objects, whether we're talking about words in a language model or items in a recommender system. The idea is elegantly simple. By looking at the angle between two vectors, we presume that smaller angles indicate greater similarity. It's a measure that's easy to compute and interpret, and its popularity is well-deserved in many practical applications. However, as our researchers Steck, Ekanadham, and Kallus delve into, the reality is a bit more nuanced. Their work uncovers that cosine similarity isn't always the reliable indicator of similarity that we might hope it to be. In certain contexts, especially when dealing with embeddings derived from regularized linear models, cosine similarity can produce arbitrary and, frankly, meaningless results. This isn't just a rare glitch. It's a fundamental issue stemming from the very way we train our models. Let's unpack that a bit. When we embed discrete entities into dense vectors, we're essentially mapping complex high-dimensional data into a space where mathematical operations become feasible and meaningful. The process often involves training models with regularization techniques to prevent overfitting and ensure generalizability. But here's the kicker. The type of regularization employed can have unintended consequences on our similarity measures. In their analysis, the authors explore two primary regularization schemes. The first applies regularization to the product of the embedding matrices directly, while the second regularizes each matrix separately. It turns out that the former can introduce an arbitrary diagonal matrix into the cosine similarity calculation, leading to non-unique and potentially meaningless similarity scores. In contrast, the latter approach results in unique cosine similarities, but it leaves us wondering if these similarities truly capture the semantic relationships we aim to measure. This brings us to a critical implication. The very foundation of how we compute similarity might be built on shaky ground, depending on our modeling choices. For practitioners, this means that blind reliance on cosine similarity could lead to misinterpretations of data, affecting everything from search algorithms to recommendation engines. But fear not, it's not all doom and gloom. The researchers don't just highlight problems, they also propose remedies. One solution is to train models with cosine similarity in mind from the outset, possibly through techniques like layer normalization. Another approach is to project data back into the original space before applying cosine similarity, thereby bypassing the problematic embedding space altogether. Additionally, mitigating popularity bias and standardizing data can help ensure that cosine similarity remains a useful tool rather than a misleading one. Their experiments, conducted on simulated data, reinforce these theoretical findings. By manipulating regularization methods, they demonstrated how cosine similarities can vary wildly even among low-rank embeddings. These results serve as a cautionary tale against the uncritical use of cosine similarity, urging us to consider the underlying mechanics of our models more carefully. For those of us entrenched in machine learning and data science, this research serves as a valuable reminder. It challenges us to question the tools we take for granted and to seek a deeper understanding of the metrics that drive our models. As we continue to develop more complex and deep learning models, the interplay between regularization and similarity measures like cosine similarity will only become more intricate, necessitating ongoing scrutiny and innovation. In closing, the work of Steck, Ekanadham, and Kallus invites us to rethink our approach to measuring similarity in embeddings. It underscores the importance of not just relying on established metrics, but also understanding the conditions under which they operate effectively. As we advance in our quest to model and interpret complex data, such insights will be crucial in ensuring that our tools serve us as accurately and meaningfully as possible. Thank you for joining me in this exploration of cosine similarity and its role in modern machine learning. Until next time, keep questioning, keep learning, and keep pushing the boundaries of what's possible.